Hello, I'm Martin Woolley from the Bluetooth Special Interest Group. I'm talking to you today from my home office in the UK, and for today's talk I've selected a number of different topics, largely because they give me an excuse to look underneath the APIs and talk more about how Bluetooth works, what's really going on, and how to get the best out of it in certain application scenarios. So I'm going to start by just getting everyone orientated, and we'll cover a few of the basics, and then we'll move on to some more advanced topics. So there are two Bluetooth communications technologies. They're branded in the same way, so this may not be obvious. The older version of Bluetooth is called Bluetooth BR-EDR. That's basic rates, enhanced data rate, and it's basically a cable replacement technology that allows communication directly between two devices. But then we've got Bluetooth Low Energy, which is newer, it's much more power efficient, and it's a lot more versatile. So it can form point-to-point connections between two devices, but it can also broadcast data, which means that an infinite, absolutely unlimited number of devices in range of a transmitting device can receive whatever is being sent. Pretty powerful stuff. And then we also have Bluetooth Mesh, which is a networking technology for forming mesh networks in places like smart buildings. It actually uses Bluetooth Low Energy under the hood, but the top part of the stack is completely different and is all about networking rather than just data communications. So I'm going to focus on Bluetooth Low Energy here in this talk. So let's start with some basics. Typically, a smartphone application will need to go through a number of steps. It will need to discover and filter out and determine relevant devices that are in range, probably offer them to the user for selection, and then connect to it and interact. So the way this typically works is peripheral devices do something called advertising, and advertising involves broadcasting small amounts of information about the device, maybe its name, maybe some hints about its capabilities, and your application will receive all those advertising packets and figure out which are coming from devices that are relevant to your application, present the user with a list, and then we move on to the sort of next stages. Now, Android has some great APIs. The key ones you'll be using here are Bluetooth LE Scanner. That's how you actually kick off the scanning process. But you can also specify some settings to do with performance and some filtering criteria, so you only get told about seemingly relevant device types. So once a device has been selected, you'll then connect to that device, and at that point it will almost certainly stop advertising because it's now in what we call the connected state. Now, once you're in a connection, you're going to be working with a table of data on the remote device called the attribute table. Now, sitting inside this table are a series of attributes, hence attribute table. And each attribute in the table is of one of three types. There are services, characteristics, and descriptors, and collectively they form a hierarchical structure. Now, services act as grouping mechanisms, and they contain characteristics. Characteristics are really just data items which have a specific type identified by a UUID. They have a value, and they support various operations that the remote connected device can initiate. Things like reading the characteristics value, writing to it, or enabling something called notifications, which when switched on result in the characteristics value being delivered to your connected application whenever it changes, or maybe periodically controlled by a timer. Now, at the third level of the hierarchy, we have descriptors, which only some characteristics have. They allow us to do things like switch on or off notifications, or they provide metadata which further describes the characteristic in some way. So as you can see, you have a bunch of Android classes which represent these attribute types, and the Bluetooth GATT class, which provides a kind of facade API to the various operations that you can invoke. Now, GATT itself is a technical term. So the Bluetooth Low Energy stack on an Android device looks like this. It's got two major components. You've got the top part in blue, which is called the host. It contains various layers of the protocol stack, and underneath it we have the controller, which contains layers from lower in the stack, partly concerned with controlling the radio receiver transmitter hardware in your smartphone. Now, as an application developer, most of your interest will typically be in the top layers of the stack. The APIs you use will largely be concerned with GAP and GATT procedures and use the attribute protocol to have a conversation between the two devices. So GAP is the generic access profile, and it's concerned with device discovery and forming connections. And the generic attribute profile, or GAT, is concerned with procedures that involve the attribute table. So you'll see the word GAT in some of the API class names. So GAT procedures are executed through attribute protocol PDUs, that's protocol data units, that are exchanged over the air between the two devices. And so when you call an Android API, what you're usually doing is driving a GAT procedure, which will result in an exchange of one or more attribute protocol PDUs between the two devices. So what I want to do now is take you through a number of topics, and I'm going to start here with the subject of reliability. Now, we could probably do with a definition to start with, but a very simple definition of reliability in the context of communication is that data that we send is the data that is received. We could go further and get a bit more nuanced. We could talk about latency. We could talk about maybe having a tolerance for a certain number or percentage of failures. We could talk about resilience and so on. But the data sent is the data received will do for our purposes today. Now, Bluetooth is a radio-based wireless communications technology, and radio itself presents all sorts of challenges in achieving reliable communication. So here's my first example. When a device transmits data, it does so on a selected radio channel. And if another device transmits using the same channel at the same time and is in range, the two transmissions will collide, and collisions cause corruption of the data. It's just like having two different coloured lights in a room, and if you switch them both on at the same time, the colours will mix, which in my example here, you can see I'm using red and blue, will result in purple. So the original data is effectively lost. And the same kind of thing can happen with radio transmissions. Now, the busier the radio environment, the more devices and the more verbose they are, the more likely it is that you'll experience collisions. Another couple of related issues are called coexistence and co-location. So coexistence refers to the fact that there can be many different wireless communications technologies actively being used in the same environment and using the same radio band. So the one that's used by Bluetooth is called ISM, that's the Industrial, Scientific and Medical band, and it starts at 2.4 gigahertz, and it's quite commonly used because it's free. Wi-Fi uses it, cordless phones use it, even microwave ovens use it. So all that activity in the same radio band can give rise to interference and cause reliability problems. Co-location is not completely dissimilar, but it refers to the use of multiple wireless technologies inside the same device, and there can be interference within that device as a consequence, and smartphones are a very good example of device types that use multiple wireless technologies. So now I'm going to talk about some of the ways in which Bluetooth technology addresses these kinds of issues and essentially creates reliable communication, albeit from potentially very unreliable foundations. So the first thing to understand is the modulation scheme. Now, a modulation scheme is a way in which the fundamental properties of radio waves can be harnessed to encode digital data. So in our case, we use something called frequency shift keying. And frequency is one of those fundamental radio properties, and compared to other modulation schemes, such as those based on amplitude, for example, it is better at resisting interference. So choosing a frequency-based modulation scheme was a good choice for Bluetooth right from the start. Now, the way this particular scheme works is that given a particular radio channel, which is defined by a range of radio frequencies with a lower bound and an upper bound, you take the central frequency, and if you want to send a digital 1, you shift that central frequency up by a given amount called the frequency deviation. And if you want to encode a 0, you subtract the frequency deviation from that central frequency and transmit on that frequency for a period of time. That's basic frequency shift keying. Now, making abrupt changes of frequency can generate noise though, and that's a problem because that causes interference, which causes reliability problems. So the Gaussian part of the Gaussian frequency shift keying modulation scheme that Bluetooth uses involves applying a smoothing filter to frequency changes so they don't generate noise and we have a reliable basis for encoding data and for communication. So let's have a look at what we're actually transmitting. On screen you can see what we call the air interface packet. The structure is always the same, the payload can vary, and some of these fields are specifically there to help us achieve reliable communication. So you need to imagine data arriving one bit at a time in a serial fashion at the receiver. So starting from the left, the first field is called the Preamble. It's 8 bits and it consists of a pattern of alternating ones and zeros. So this helps the radio, which is scanning across the range of frequencies in the selected channel, to identify exactly what frequencies are being used to encode those ones and zeros by the transmitting device. And once we've locked into these frequencies, we next have the access address. So at this stage of the game, the radio receiver is receiving everything transmitted on that channel. So we're talking about signals that are not related to Bluetooth at all. We're talking about Bluetooth transmissions that are not intended for this device. So the access address provides a unique identifier for a connection between a pair of devices, and also a way of indicating that the transmission is for all Bluetooth devices in range, say for when we are broadcasting. So this helps us separate relevant transmissions from irrelevant. If we shift our attention to the right-hand side of the slide, the cyclic redundancy check is on all packets, and its job is to provide a way which allows data corruption to be identified. So errors in communication are picked up by looking at the cyclic redundancy check. The way it works is that the transmitter formulates its air interface packet consisting of a number of bits. It then calculates a CRC value from all of those bits in the packet and adds it to the end and then sends it. So the receiving device goes through the same process and calculates the CRC based on the bits it received, and it compares the calculated CRC with the received CRC in the packet. If they're the same, we conclude that we're okay, no corruption has happened. If they're different, we have to conclude that something bad has happened, or we've lost some data somehow. And typically what happens then, controlled by certain layers of the stack, is the packet is not acknowledged, which prompts the remote device to send it again. So finally, we've got something called the Message Integrity Check Code, or MIC. It's not really a reliability feature as such, it's really a security feature. It's a cryptographic message authentication code that allows us to detect if encrypted packets have been tampered with. So remember that data could be changed in broadly two ways. One way is accidentally through things like environmental issues, and the other is deliberately with malicious intent, and the MIC protects us from those sorts of changes. So Bluetooth uses something called spread spectrum in a number of different ways, and it's the name for a set of techniques that involve distributing packet transmissions across multiple radio channels, usually with the sole intent of achieving reliable communication, especially in busy radio environments. So Bluetooth Low Energy uses several spread spectrum techniques, and we'll discuss some of those now. As you can see from the slide, the ISM band gets divided into 40 channels, each of which is 2 MHz wide. Now, when two different devices are connected, various interesting things happen, but one of them is that a process called adaptive frequency hopping takes place. And this is one of the spread spectrum techniques that Bluetooth uses. So what you can see on screen is a histogram showing the number of packets sent on each radio channel during some testing that I was doing. You can see that communication was spread right across the ISM band, except for in 3 places, because 3 of the 40 channels are not used when in a connection. So 37 of the channels are used when performing adaptive frequency hopping in a connection, but 3 are special and they're reserved for connectionless communication or advertising, which I'll come on to. So the channel changes at agreed intervals, and it can be as often as every 7.5 milliseconds. And the adaptive part of the adaptive frequency hopping technique refers to the fact that devices can determine how well each channel is working and which are subject to interference and not working well. Based on that information, the system then optimizes its use of channels and avoids those which are not working well. So connected Bluetooth devices work really well, even in very busy radio environments, because they dynamically figure out which channels are working well and which ones are not and should be avoided. Now, when we're doing connectionless communication, the three special channels 37, 38 and 39 are used. And basically a copy of each packet gets broadcast on each of these channels, usually in some random order, one at a time. We also randomize the timing of these transmissions slightly because this helps us avoid persistent collisions. You can also do something called extended advertising, which allows additional data associated with the main packets to be distributed across the other 37 general purpose channels. So this is spread spectrum, working in a not dissimilar way to adaptive frequency hopping, but applied to connectionless communication. And this is a screenshot from my protocol analyzer, and it's showing you standard advertising taking place on the three advertising channels. Now, those channels were deliberately chosen in the design of Bluetooth to be spread far apart in the ISM band to avoid Wi-Fi and to ensure that even if one end of the spectrum, say, is completely saturated because of some other wireless technology, other parts of the spectrum are likely to still be working, and so our broadcast packets will still get through on those other channels. So that was just a brief look at some of the key, most important reliability issues and how they're addressed by Bluetooth. So change of topic now. We're going to talk about how we can maximize data transfer rates with Bluetooth Low Energy, which is sometimes a requirement. Bluetooth Low Energy is usually about small amounts of data from things like sensors, but every now and again we have larger amounts of data we want to transfer, and if for no other reason than to improve the user experience, we want to do that as fast as we can. So some things to understand. First of all, radio is analog. Always, don't be fooled by terms like digital radio. Ultimately, it is all analog. And the physical layers of the stack exploit certain properties of radio waves to encode digital information, which you already know about. We've talked about the modulation scheme early on and how we use frequency shift keying to represent ones and zeros. Now, the analog representation of a bit transmitting on a particular frequency for a certain amount of time is called a symbol, and the rate at which symbols can be transmitted is called the symbol rate. So by default, Bluetooth Low Energy operates at 1 million symbols per second, and there's a variant of the physical layer of the stack called LE1M which provides this, and all Bluetooth Low Energy devices must support this symbol rate. So what do we really mean by application data rate? Well, on screen you can see a packet and its contents, and in this example only 2 bytes highlighted in yellow here are my application data. The remainder is made up of fields relating to the Bluetooth protocols that are in use. So the proportion of application data in this packet is quite small, and if we calculate the application data rate using the 1 megabit per second bit rate used by the radio, we find that we're only getting 95k bits per second for our application data in this example. Now, because the absolute amount of protocol data in each packet is fairly constant, it's the proportion of application data in each packet that most influences the data rate as measured at the application layer. So this is one of the key ways in which we can influence the application data rate. The larger the packet and the more application data in each packet, the faster will be the application data rate. Now we can increase the packet size by manipulating something called the maximum transmission unit size, or MTU as it's commonly known. So the attribute protocol is what's usually involved under the Android APIs, and the attribute protocol has an associated MTU, but it has a PDU that lets you negotiate a larger MTU size between 2 devices, and you can drive that from your APIs. Default MTU size is only 23 bytes, but you can usually go much higher on newer devices anyway. 512 bytes is the maximum, but what you get is device dependent. So if we drop down one layer in the stack to the L2 cap layer, and I've got a depiction on screen there of where L2 cap sits in the stack, just to remind you, right underneath the attribute protocol, we have a similar issue. L2 cap has its own MTU size, and its job is to pass packets to the link layer down in the controller, having received its packets from the layer above the attribute protocol. So what L2 cap usually has to do, because each layer has its own MTU, is it has to split attribute protocol packets into smaller link layer packets through a process called segmentation. And of course, this increases the protocol overhead because we end up with more packets. And we don't want this if our goal is to maximize application data transfer rates. So Bluetooth version 4.2, which is quite old now, introduced something called the LE Data Packet Length Extension feature. And this allows larger link layer packets to be used and so reduces the protocol overhead in the way that we need. And it's used automatically if both devices support it. Now, connection events are a very important concept in Bluetooth. So we have one radio only, one physical radio, and it's potentially going to be used by multiple connections to other devices. So it has to be shared somehow. So the way the system works when two devices connect, they negotiate something called a connection interval, which defines how often they're going to have access to their radio. And every time that interval comes around, we have what we call a connection event, and that's when this connection is serviced. And then the two devices kind of take turns in transmitting and receiving. Now, it's not quite that simple in practice, but it's along those lines, and that's good enough for today. Now, a connection interval can be anything from 7.5 milliseconds to 4 seconds. So that's a huge variation. If we want to maximize throughput, then obviously we want to give our connection the most frequent access to the radio that we can, so it can transfer its data as often as possible. Now, you may or may not have the ability to completely control the connection interval from a particular platform, but in the case of Android, you don't. All you can do is kind of hint that you want to go as fast as possible, or that alternatively conserving battery power is more important to you, in which case you'll get a lower connection interval. And on screen there you can see the kinds of variables or arguments to some of the method calls that are available to you. You can request balanced high or low power, which effectively gives you something in the middle, a fast connection interval or a slow one, depending on your priorities. So as you know, by default, Bluetooth Low Energy operates at 1 megasymbol per second at the physical layer, but Bluetooth 5 introduced a new kind of variant of the physical layer, which allows communication to take place at a symbol rate of 2 megasymbols per second. So that's twice as fast. So you'd expect that with double the symbol rate, the application data rate will be faster. And of course, it almost certainly will be, but it won't be twice as fast because there are lots of other variables at play here. If our connection interval stays the same, but the packet scheduler on your phone doesn't take advantage of the fact that it's using LE2M, and therefore each packet takes half the required time, and therefore twice as many packets could be sent in each connection at each connection event, then you probably won't see much of a difference. And packet scheduling falls outside of the Bluetooth specifications. It's an implementation detail that product manufacturers need to take care of themselves. Nevertheless, LE2M probably will give you faster data rates, and it will improve spectral efficiency because you'll have packets in the air for a shorter period of time, so there's less chances of collisions, better reliability in busy environments, and so on. Now, from an Android point of view, you can see there's an API called setPreferredPHY, and you use that to indicate that you'd like to have use of LE2M. Now, it depends whether the other device supports it or not as to whether you actually get that, but that's the way you go about requesting it. So last thing to be aware of where throughput is concerned is this. The attribute protocol, remember, pretty much sits under all your APIs, and it supports two ways of writing data to a characteristic. So writing data to a characteristic is likely to be how we transfer data from one device to another. So we have write commands. They're very fast, but they may be unreliable, and that's worth understanding. Ultimately, the attribute protocol runs over the link layer lower down in the stack, and there's a system of acknowledgements at work there. So a device will be informed if its transmitted packet was received by the other device, and it can deduce that it wasn't because it won't get an acknowledgement. But it won't know if a packet containing an attribute protocol PDU made its way all the way to the top of the stack to the application. So you can send write commands as fast as you want, and there could be buffer overflow at the remote device, so you have to be careful there. Be aware though that the very newest version of Bluetooth, Bluetooth version 5.2, includes something called the Enhanced Attribute Protocol, which amongst other things introduces flow control, and that makes write commands both fast and reliable, but older versions don't have that flow control on write commands. Now, the other way of writing data is using write requests, and they have a corresponding response PDU. So that makes them reliable because they are transactional in their nature. But they're also very slow because you have to wait for each response before you can send the next request. Now, assuming a characteristic supports writing at all, it will support one or both of these different types of write operation. If it supports only one, the Android API will figure out the way to proceed automatically. If it supports both, you can use the setWriteType method of Bluetooth GATT characteristic to select the one you want to use. And of course, you make that choice based on whether reliability is most important to you or speed. In many applications, a drop packet here or there really doesn't matter. In others, it might be critical. So here's a summary. These are the primary variables and associated APIs that can affect the data rate. A larger MTU is really going to help. Data length extensions, they're either supported or not. They need to be supported by both devices to be available, and they'll get automatically used if they are. Shorter connection intervals are going to give you more opportunity to send data over your connection, and you'll probably get an improvement in throughput if you use the LE2M physical layer variant rather than the LE1M 1 megasymbol per second default. And you can see there are various Android APIs there that I've thrown up onto the screen just to give you a quick reference as to where to look in the API reference documentation. So I did some benchmarking with an Android application I wrote involving the transfer of 100K of data from my smartphone to a peripheral device using, first of all, write commands and working with the defaults that Android provided me with. So that was an MTU of 23 bytes, that's the default. I was using the 1 megasymbol physical layer symbol rates, and I was allocated a connection interval which I was able to see to be 48.75 milliseconds using my protocol analyzer, and consequently it took nearly 8 seconds to transfer my 100K of data to the other device. Now, when I took control using the Android APIs and chose a larger MTU size, selected the 2 megabit per second symbol rate, and chose the shortest connection interval available, I was able to reduce data elapse time down to just over half a second, which is a huge improvement, as you can see. Think about user experience there. Now then, I did the same thing, but I used write requests and responses rather than write commands. And as you can see, it took a huge 500 seconds using the defaults, but with some tweaking, I got that down to about 10 seconds. So big improvement there as well. And again, you're going to have to decide whether reliability or speed is your priority. So moving on, let's talk now about range in Bluetooth Low Energy. And I think that for historical reasons, most people still think it's about 10 meters or maybe 20. That's most certainly not the case though these days. Lots of things have changed over the 20-year history of Bluetooth, and range is one of them. So the first question to answer is, if you want to really understand the subject of range, is what is it exactly that limits range in wireless communication? What's the problem? So it's natural to assume that transmission power is the only variable affecting communication range. After all, if we want to throw a ball further, we throw it harder with more power. But regulations mean that there is a limit to how high the radio transmission power can be set. It also probably seems natural to assume that if a device is out of range, that's because its transmitted signal can no longer be detected, but that's not necessarily true either. So this is how range limits really work. On the screen, you can see a blue line representing the strength of a transmitted signal getting weaker and weaker as we measure it further and further away from the transmitter. Now, as you can see, it reduces in a non-linear fashion, in fact following an inverse square law. Now, the red line represents the level of background noise which is always there. This is electromagnetic radiation from natural and unnatural sources. Now the problem with range is that the nearer the transmitted signal strength gets to the level of the background noise, the harder it becomes to accurately decode the data in that transmission. In other words, the lower the signal to noise ratio becomes, the more errors we will encounter, and we can actually measure this through a concept called the bit error rate, or BER. Now the Bluetooth specification states that a BER of less than 0.1% is required. So if the error rate starts to exceed this limit, then we no longer have functioning communication. It's at this point that we say we're out of range and the connection will drop and things like this. So different radio hardware will perform better or worse in this respect. And the minimum signal strength in dBm at which the BER remains below the magic 0.1% is called the receiver sensitivity. So different devices have better or worse receiver sensitivity, and that's a factor of the hardware rather than the Bluetooth stack itself. So you should already know, of course, how errors are detected using the cyclic redundancy check, which every packet has. But there's a capability of the physical layer that was introduced at Bluetooth 5 called the LE-coded PHY, and it goes a step further because using extra data included in each transmitted packet, the receiver can employ a mathematical procedure called forward error correction, or FEC, and it can actually correct bits that are found to be in error. So this means that we can stay below the maximum bit error rate of 0.1%, even when the signal to noise ratio is getting very low, and therefore we can continue to communicate effectively at much longer ranges. Now in practice with the LE-coded PHY, up to 4 times the usual range is possible, but be aware that FEC adds quite a lot more data and can reduce the effective physical layer data rate down to 125 kbits per second from the usual 1 megabit per second, depending on how you use it. So it's a trade-off between data transfer rates here and range. There's no such thing as a free lunch, people. So let's summarise. Without FEC, diagram not to scale, by the way, the numbers don't mean anything, but without FEC you can see that we basically reach our maximum bit error rate, which is the black line, at a certain distance from the transmitter. Again, none of this is to scale. But if we use forward error correction with the LE-coded PHY, what happens is that we can go much lower in terms of how close we get to the signal to noise ratio, and this gives us a much longer range. In fact, over 1 kilometre is possible, and there are videos on YouTube of people demonstrating this, so you can go and look if you like. In fact, I met a company last year who had achieved 3 kilometres in their testing of one of their products, which is pretty amazing, certainly more than 10 metres. So here's a quick summary of parts of the Android APIs that relate to Bluetooth and range. We can find out whether our device supports the longer range LE-coded PHY or not, indicate that we'd like to use it if the other device also does, and we can kind of control the trade-off between range and the physical layer data rate using a parameter called S. So we're either going to double the range more or less and reduce the data rate to 500 kbs, or we may go for 4 times the range approximately, and we have to reduce the physical layer data rate to 125 kbits per second in doing so. It's all good. So, new topic, let's talk about Bluetooth Mesh. If you're not familiar with Bluetooth Mesh, this is a relatively new technology that lets you create whole networks of literally tens of thousands of smart devices. Initially it was designed for use in smart buildings with lots of sensors and automation driving things that happen in the building. So the Bluetooth Mesh stack is not quite the same as the one I showed you earlier on smartphones and peripherals. That's what you can see right now. It uses the Bluetooth Low Energy controller, but the host contains different layers of the stack, and they're all concerned with mesh networking. Now you don't have this stack variant on an Android device, so there are no APIs for Bluetooth Mesh in Android either. But why would you want to use Bluetooth Mesh for an Android application anyway? Well, consider a smart building full of wireless lights, switches, sensors, air conditioning systems, automated blinds, and heating systems, and so on, lots of things. There's a need for user interface applications to be used by people for monitoring, control and configuration purposes. And this is where Android applications can be ideal. But if you don't have Bluetooth Mesh APIs on your Android device, how can you do this? Well, luckily we did think of this, and the answer lies in the fact that Bluetooth Mesh defines a number of special networking roles that any device that are a member of a network can play. And these roles, one of these roles is called the proxy role, and it's very simple because a node or device acting as a proxy has both the Bluetooth LE stack that you have on an Android device with support for GATT and GAP and the attribute protocol, and the full Bluetooth Mesh stack, so it can kind of translate between the two. So your Android application will scan for proxy nodes which advertise themselves, connect to one, and then send and receive Bluetooth Mesh messages by writing to a characteristic that the proxy node has in a GATT service called the Mesh Proxy Service. Or it can receive Mesh messages back, kind of wrapped in things called notifications, which characteristics can generate. And all those things to do with GATT, of course, are supported with your APIs. So this slide hopefully shows well enough how this works. We've got a Mesh proxy node in the middle there, which is part of a Bluetooth Mesh network. It's not a dedicated device, by the way. It could be a light or a thermostat, but it's also been configured to act as a proxy. So as you can see, it implements the Mesh Proxy Service, and it contains two characteristics. One which you can write to over a connection to inject a Mesh message into the network, and one you can receive notifications from containing Mesh messages. So there's some kind of tunneling going on here. So for the Android developer, everything is familiar really, and no difference to discovering, connecting to, and then working with the characteristics on any connectable Bluetooth Low Energy device. The only new thing you need to know are a few Bluetooth Mesh networking concepts and exactly how those characteristic values are structured so as to properly represent Bluetooth Mesh messages. And I'll point you in the right direction for more information on this shortly. So what about the future of Bluetooth? Well, Bluetooth evolves all of the time. There's always a lag between a new feature appearing in the Bluetooth specifications and it becoming available on platforms via APIs. So here are a couple of newer things to look out for in future releases of Android, hopefully. So Bluetooth Low Energy now has a direction finding capability which you can use in a couple of different ways. The first is known as angle of arrival, and the second is called angle of departure. And it lets you determine the direction a signal is being transmitted from, and from that you can determine the location of objects to within 10 centimeters. And this works indoors, out of sight of GPS satellites which we might otherwise rely on. So it's for higher accuracy, indoor location-based services like wayfinding and asset tracking. LE Audio was announced early this year. Now, it's still the case today that the most common use of the old Bluetooth is in audio products like headsets, headphones, and so on. But it has some limitations. And so LE Audio was introduced to address those limitations. The old Bluetooth audio we now call Classic Audio, and the new Bluetooth audio is called LE Audio because one of the changes is that it uses Bluetooth Low Energy. It also has a new codec, new audio codec, which is higher quality than the one used with the old Classic Audio. Far more interesting, in my opinion, is it supports new use cases. So instead of being constrained largely to kind of one-to-one, point-to-point scenarios, phone to headphones, for example, you can do things like broadcast music. So you can share music with a select number of friends in a small group. You can broadcast privately with access via a passphrase or password or something like that. So you could use it in things like cinemas or at the opera, if you're so inclined. You can do public audio broadcasts, which anyone can hear as well. And with any broadcast or connection-based communication to individuals, it supports concurrent delivery of multiple content streams. This is quite amazing. So you could have different language versions of the same content being transmitted concurrently to a group of people. Really, really quite powerful stuff. And the other thing to know is Bluetooth's new LE Audio will bring to the world of hearing aids a standard for wireless hearing aids, which has been lacking so far. A lot of the companies involved in working within the Bluetooth Special Interest Group's working group on this subject came from the hearing aid industry. So LE audio is going to be huge. It's not in products that I've seen just yet, but it will be, and it's going to make a big splash, I'm sure of that. Now, under the hood, this was all enabled by something in the Bluetooth core specification called Isochronous Channels. And isochronous channels are a way of communicating data which is time dependent. So I could send the same data to multiple devices, and those devices would know that they needed to render or process that data at exactly the same time. And that's how concurrent distribution of audio data to lots of different devices ultimately works and gives the right kind of audio experience. So where next? If this has been interesting, if you'd like to know more about Bluetooth technology, largely with the idea of designing or developing products, guess what? We've got lots of good stuff at our website, which of course is bluetooth.com. So if you go to our resources section and click on study guides to filter the list there, you'll find things which are aimed at providing a kind of self-paced, self-study framework for developers looking to learn about certain areas. Some of my favorites are on screen there. They almost always have some hands-on development projects in there amidst all the theory, so you get to kind of learn by doing and consolidate your understanding by actually writing some code, maybe building a device as well. Lots of papers as well. So papers are an easier read than the specifications. They're intended to introduce you to subjects. So if you're short of time and just want to get your head around something new, go look at some of the papers. There's some really good stuff there, which I think will meet the need. So that's it from me. Thank you so much once again for attending and listening to today's talk. I think we should have time for some questions. If not, I'm on Twitter, so feel free to ping me a message and I'll get back to you as soon as I can. Thank you once again.